In a previous video, we have discussed the stability of carbocations, and due to hyperconjugation, tertiary carbocations are more stable than secondary, and those are more stable than primary, and even more stable than metal, in which we have 3 hydrogens. Now, we now are going to study carbocations rearrangement. And that happens when the skeleton of the molecule is going to be changing to form a more stable carbocation. So let's talk about that, but with an example. Say that I have this carbocation. If we look at our definition here, focusing on where the positive charge is, you have one R group here and one R group on the other side. So that is a secondary carbocation. Now remember that in line structure, here you have 3 hydrogens, and here you have 2 metal groups, which means you have a hydrogen here. So now, what happens now is that we can have what we call a hydride shift. And we call that a hydride shift. This is a 1,2 hydride shift. And when we say hydride, we're moving this hydrogen with the electrons. And in doing so, now the resulting structure, because the hydrogen took the electrons, right? So it is a hydride shift. Now we're creating a positive charge here. And the hydrogen will be moving over to that side. So now I'm going to have another hydrogen. Before I had only one, now I'm going to have 2 hydrogens, say that was. I'm just drawing those explicitly so that you remember that. You have moved 1 hydrogen over there, and let's draw just the one that was originally there. So the initial structure is this, but what I'm doing here is drawing the hydrogens explicitly so that you see that we have moved 1 hydride over to the other side. Now, analyzing where the charge is, this carbon is attached to 1, 2, and 3 R groups, so that is tertiary. So that rearrangement happens because we are now creating a carbocation that is more stable. And that's always the case. So carbocations are going to happen, they will happen if you can form a more stable species. And they will not happen backwards. In other words, you never go and see a rearrangement from tertiary to secondary. It's always getting to, say, least stable to more stable. So now we have said 1,2 hydride shift, meaning from neighboring position, right? So right next to the positive charge. And again, it's hydride because you're moving the hydrogen with the electrons. Now let's do something else. Say that I have now this. In this structure, we see that the carbon here where the positive charge is attached to a metal on the side, and here you have another R group, ethyl butyl. So it is a secondary carbocation. As we see here, it's not as stable. Let's see if we can make it better. Now, at the carbon, the neighboring carbon, we don't have a hydrogen, so I cannot do a hydride shift. But there is another type of rearrangement that happens, and that is a methide shift. So we can have also 1,2 methide. What that means is that the metal group is going to move with the electrons. And the resulting structure after that movement is the following. So I'm moving, again, metal with the electrons is a methide. So, and in doing so, I am creating a positive charge here. And now I have the following structure. That's the structure that results after the 1,2 methide shift. Now, carbocation is now the carbon here attached to 1, 2, 3 R groups. So it is tertiary. So this rearrangement will happen because we're going from a secondary to a tertiary that is more stable. And that's always, again, the case. So essentially, we have this type of carbocations. Now, we're going to be applying that to reactions and see, because this topic is important, because in any reaction that you form carbocations, and examples of that may be an SN1 reaction, or say, for instance, in the case of an alkene undergoing addition, Markovnikov addition, for example, we form carbocations, and not always the major product is what you obtain attacking directly the carbocation that's initially formed. We sometimes have rearrangement, and we need to take this into account. That we're going to see in problems of these reactions.